I'm very pleased to welcome Frédéric Boudon. Frédéric is a researcher from CIRAD in Montpellier, so International Center for Agronomical Studies. And Frédéric is, let's say, the father of the LPI system. He's the lead developer, and he nicely accepted to contribute to this training session. Actually remotely, but still, thank you very much, Frédéric. And Frédéric wanted to explain some recent work that he made on the adaptation of LPI to its use in notebooks, in Jupyter notebooks. So it's a different way of programming L system that we saw during the previous days in the training session. And you will see how you can use these notebooks in order to program the development of plants. And I think Frédéric will explain the programming of functional structural models with the L system in the context of notebooks. Thank you very much, Frédéric, and the floor is yours.
Thank you very much, Christophe. So indeed, I will try to present you our recent work on the development of what we call virtual modeling environments. So indeed based on notebooks. So the idea is now to go beyond the use of a personal computer and being able to create software environments that can be run remotely and can be distributed anywhere. So for this, indeed, we will use a notebook. So first, I need to say that this work is not only mine. It was also made with Yann Vaillant, an engineer which was hired in CIRAD and which was based on Réunion Island. And it was also with the help of other colleagues from the Ortiz lab in Réunion Island. Okay, so even if it's a remote session of training, all the material has been put on GitHub. So on the following address, github.com/FredBoudon Romic trainings. So for this, you can download the materials with Git as usual. Inside, you may find some files which describe all the software modules that are needed for these sessions into the file environment.yamls. And so you can create software mini Conda environments with this. It is to note that because it is a virtual modeling environment, it can be also played online. So on this page, you will find also some links where the notebook can be played on the Binder servers. Okay, so if anyone wants to play these different examples that I will show, they can be played directly online. Okay. So now to give a bit of context, so you have, in theory, with these sessions, you have LPI, which is a software environment, which allow to define some FSPM models. It is not the only one. Within the FSPM community, there is a variety of dedicated modeling software. So for instance, VLab and LStudio, which has been developed in Canada, or GrowImp in Germany. There is many others. Most of them have dedicated modeling paradigms, such as gross grammar, or some of them are more simple with, for instance, some R models. In general, these modeling frameworks allow some interactive visualization of the 3D structure of the plants. They allow also, in general, some interactive editions of the models by, for instance, playing with the parameters to make it possible to have an intuitive design of the model. However, these approaches suffer from recurrent limitations. In general, the modeling tools are packaged only for personal computer, and they require, again, in general, some complex installation procedure that may fail. So this makes the level of reproducibility quite poor in terms of software. Moreover, even in terms of model definitions. The model in general describes the code of the model is in some source code repository, and the hypotheses and results of the models are described in a separate document, such as a paper or a scientific article, or reports. So again, the reproducibility is quite poor. So to define more clearly what we call computational reproducibility, there have been, so this is an active research field right now, and there have been different levels of reproducibility that have been identified and described in the literature. A first level consists of repeating the same virtual environment using the exact same settings. So for this, we need an extensive recording of the information, including the data, the parameters, and the software environments, and possibly the hypotheses, the results that are achieved. The second level consists in replicating the experiment using similar settings, but for instance, with a newer version of software, so with a slightly change in the configurations, but based on the same definitions. Finally, an experiment can be reproduced when it uses the same specifications, but different implementations from the original ones. Sorry. An additional level consists in reusing the experiment for a different or extended objective. So you're reusing the same codes, but for a different purpose. So with classical approaches, such level of reproducibility are in general difficult to achieve, and so alternative approach need to be defined. So in this spirit, these last years have seen the emergence of a new way to communicate scientific idea using notebooks. So in these environments, the codes is interspersed with charts, figures, text, and equations to describe exactly the model. So this allows to create what we call a computational narrative, where the analysis of the modeling scenario is described textually and with visual elements alongside their codes. Some interactive features allow even to manipulate different parts of the model and its parameters. The concept of literal programming was originally introduced by Donald Knuth in 1984, and notebooks were introduced in a number of commercial packages, such as Mathematica, Maple, or later in open source software such as SageMath. More recently, the Jupyter project, an open source interactive computational notebooks, has exploded in popularity. As many good open source software, it started from the PhD as a side project of the PhD, the one from Fernando Perez. Its strength comes from proposing a clear and open format for its notebook representations using JSON. And thanks to a major redesigns of the software in 2015, it was possible to couple it with many programming language. And for instance, the name Jupyter stands for a mixture of the name Julia, Python, and R. And I think nowadays there is something like 100 languages which are possible within Jupyter. So I don't know. So this notebooks has been discussed in many famous scientific journals such as Nature or PLOS Computational Biology. So it starts to become somehow standard in science to use such approach. And if we look at some activity analysis over GitHub, it shows that recently more than 9 million Jupyter public notebook was published in the last years. So a strong point of the Jupyter project was that it is based on a distributed infrastructure, and it allows us an easy deployment on the internet for instance, using the Jupyter project that allow to play Jupyter Notebook for multiple users. And there is some online services such as Binder that allow to play any notebooks using minimal configuration. So just by specifying within text files what are the software modules that are required. It also became the basis of some famous infrastructure for the access of computational resources of large companies such as IBM, Microsoft, and so on. Online resources for education were also constituted based on Jupyter infrastructures. For instance, in the Berkeley University, most of their training sessions are described using Jupyter. You can use specific modules of Jupyter to display, for instance, the notebooks as slideshow during classes. And you have also some modules to create exams using Jupyter. Some books start also to be published using notebooks, and of course, you find many scientific papers with additional notebooks as a supplementary information. The Jupyter ecosystem is quite active, and so you have now some Jupyter conference every year to discuss the future of Jupyter. So coming more to the actual software object, there is different applications with different styles that allow to interact with notebooks. So the simplest version is a shell, where you have some rich display that allow to plot some figure or even some equation or some text. The standard and most famous application is a notebook display within a web browser, with cells that you can edit or play, and with charts and equation text that can be added interactively. There is an advanced version which is called Jupyter Lab, which is also played into browsers that allow to manage different resources, customize the display, and rearranging cells according to the needs or the modeling scenarios that you want to design. If you want to make a specific demo or specific tools for user, you can also create specific web applications using, for instance, the Voila project, where you can have sliders and charts that are animated directly. Finally, as I already said, notebooks can be displayed as an interactive slideshow for didactic presentations. I will illustrate a different type of applications in this presentation. Now notebooks start to be integrated also in classical IDE, such as Visual Studio Code, that allow to display directly and edit directly as simple codes some notebooks. Okay, so this was for some sort of general introductions, and this is the general context for programming. And of course, we wanted to adapt such environments for creating reproducible functional structural plan models. But for this, a number of challenges was identified that we needed to address. So in particular, we identify 4 main challenges. First, as I already said, an important key feature of FSPN modeling is an interactive 3D visualizations of the modeled structures. However, providing such functionality into the context of distributed software infrastructures with notebooks that are played with the server notebooks and the visualization onto a web page is quite a challenge. Within FSPM, a number of specific modeling formalisms, such as generative grammars our workflow have been developed. And so we needed to integrate within this environment such formalisms. Intuitive designs of the models comes with the possibility to interactively edit some of the parameters. Again, having this into distributed environments, software environments can be complex. And so we needed to address this problem. Finally, the different software modules that are developed within the FSPM community comes from different groups, and it's not always easy to gather them into a coherent environment. So for this, we propose also a way to create reproducible and distributed software environments using some of the possibility offered by open source development tools. Okay, so what we achieved to present what I will the challenge we address and how it what are our achievements. First, we developed software modules that allow the 3D visualizations within notebooks of plant structures, also in 3D. So for this, we needed some interactive visualizations. So we really tested several solutions to have performant solutions, and I will present you what we proposed. For the integration of modeling formalisms, we first integrated L systems, which is a classical formalisms to define FSPMs, and also workflow, dedicated workflow to create software modules that can be gathered to create complex models. Sorry. Finally, we worked also on the editions of L systems parameters. So for the L systems, models will be automatically parsed, and some user control can be generated in the web clients and interactively control the simulations onto the Jupyter servers. Finally, we define an automatic packaging and deployment procedures using a continuous delivery approach for the modules of the OpenLR platform that we developed using the conda management systems. And I will rapidly present you such things. So to illustrate all of this, I will show you a number of demos. So first, I will show you rapidly how to display. I will explain you how we develop a module to display 3D scene within notebooks, and then make a small demo. So again, to recap the context, within the Jupyter framework, there is a client onto a web browser and a server that contain actually the execution of the model. And to transmit the result of the simulations, the generated 3D representation has to be communicated from the server to the clients. From the client side, actually, there is a high-level JavaScript library, 3JS, which is available and which allow to display computer graphic in the web browser. So somehow the goal was to minimize, to start from the 3D representation, which for now is in PlantGL, and to minimize the transmission times to the 3JS library. So this transmission times can be decomposed into a time to encode the representation into a streamable representations, the actual time of stream, and the time to decode these representations and transform it into a representation that can be understood by 3JS. So streaming time will be proportional somehow to the size of the data, and the encoding and decoding times will be proportional to the original 3D scene size. So somehow there is a compromise to find between the encoding and decoding times and the streaming times. So for this, we tested different approach to serialize and stream 3D representations. First, we tested the module P3JS that proposed an API in Python to represent the 3GS object and then to stream them and allow the streamings. But such approach has several limits, as it mainly addresses static representations and does not allow high-level representation for plans. So this requires to represent the plant shape with lots of geometrical details. And so this was not very efficient. As an alternative, we tested the Draco mesh compression library, which starts to be quite standard, and that propose very efficient compression algorithms. The drawbacks, again, is that it requires to convert the entire 3D representation to a single mesh and thus remove semantic informations. Finally, we tested an alternative approach that consists in using directly the 3D serialization method of PlantGL and combine it with the standard zip compression protocols. And the advantage is that PlantGL representations allow to use massively instantiations and high-level primitive for compact representations of plant structures. From the client perspective, by default, PlantGL is not integrated into web browsers. So for this, we ported the PlantGL API directly using an original the original C++ codes directly transpiled using a WebAssembly transpiler, such as so for this we use Emscripten. Actually, this last approach was found the more efficient in terms of times to stream the representations and also development, as these transpilations was quite simple to do. Okay, so for demo, I will try it. Sorry. Just one sec. Okay, so a very simple L systems where we load PlantGL, so for 3D plant representations. The small modules that we developed to have 3D representations within notebooks, so PGL Jupyter. We create a simple scenes, or we just define some sphere, and we display using the SendWidget object in 3D in the web browser. Okay, so the widget is quite simple to use. So we have a 3D view. You can control a number of aspects, such as the shadings, for instance, or the mode of display with the wireframes. You can put the 3D view in full screen if you want, and so on and so forth. You can create movie or picture of your 3D view. So you have many possibilities that standard 3D visualizations tools allow. Okay. So coming back to the presentations. So this was for simple 3D structure representation. Now I will show you how we integrated L system within notebooks in a more seamless way. So again, I have a small demo. Which is actually already here. So again, you have a number of cells, and what I want to do is to show you. Oh, it's not very pretty, but Okay, better. So this is another way to present a notebook. As I said, this is a RISE modules that allow to show the notebook as slides. So again, I have a title, a presentation of what is supposed to do the notebook. So in this case, it will model the growth of a simple growth unit. And for this, you have a number of growth functions that are defined, and at the end, some rules that are defined and displayed. So first of all, we need to import again the Plunger Jupyter modules. We have a specific growth functions which is used for this functions for this model. So this is a logistic functions. So the equation is given as a simple text. The code is given just below, some potentially some reference. With that, the parameter of the model is defined. We can have some intermediate preliminary plots where we display, for instance, the size of the leaf and the size of the internet according to the rank onto the growth unit. We can, so this was the final size. Here again, we have some codes to show the kinetics of the growth of the different leaves. Again, some plot. What is nice is that this is a very classical Python code with a classical display functions of matplotlib. So somehow we have separated some aspects of the model which are independent of the L system formalisms. And then, based on these functions already defined, we can define some L system rules. So for this, some specific commands was introduced, so %%lpi, that will say that this specific cell is actually some L system codes. Some parameter exists, for instance, to say that this is animated models, and some dimension of the display is given. Again, then after that, some axiom is given, some production rules, as you already studied that, and some interpretation rules for the 3D display. Once they are defined, they can be run, and then a 3D model is defined. So I can play it several times. We can go back to the axiom, play some step, go back in times, or go directly to the last points, and so on and so forth. So we find back all the manipulation of L systems that we have found into the LPy Studio software. So this is quite easy. This is directly integrated below the L system code, and so we can define several models at the end, or complexify the model to have different successions of simulation and being able to compare them. So this is quite didactic. Okay. So coming back to the slides. So as I said, I will not go too much in detail on that, but the L system cells are made with %%lpi, and you have a number of parameters to control the actual executions of the model. An L systems can be directly an L system that have been already defined within LPy, for instance, can directly be integrated within notebooks by saying, okay, I have an L system widget, and I will use this model, for instance, these files, lowenberg.lpy, and again, you will have the 3D display that you already saw. Okay, sorry. Okay. Now what I want to show is to notebooks, a Jupyter notebook. One of the strengths of the Jupyter notebook is that it can integrate and mix several languages. So for now, LSystem in LPy has been defined using Python by coupling LSystems and Pythons. So in this next example, I will try to illustrate that some R commands, some R codes can be used to define an LSystem models directly with Jupyter. So combining R and LPy commands can be made easily. So. So this is the same, actually, the same model as before, the growth of a gross unit, except that this times we will use a Jupyter extension that allows to mix R codes with Pythons, so the RP2 modules. So similarly to %%LPy, we have this %% command that allow to define some function using R, for instance. So the logistic function in this case is defined with R codes. We can define parameter value in R also, and we can make some plot using R commands. So the length of the leaf and internode are displayed here with some simple R functions. And now the objects that have been defined previously, so for instance, internode size, okay, they have been defined in R, but they can be integrated directly in the model, just like standard Python codes. And it will give, sorry, it didn't work. Okay. Not sure if it's easy to see, but in theory, we have the same kind of visualizations, except that at each time step, this is an R command that is called to define the value, the size of each element. Okay, I think there is some problem with the networks, but my computer, but this seems to work. Okay. To continue. After seeing different languages, now we will see how we can integrate graphical parameters in the simulation. So we will start from the same, again, the same models, except that we will integrate some graphical control over the parameters. Okay, I will try to do it like this. So I will play the different cells. So at the beginning, they are just the same, except that now I will show you these cells, which show that, which define different parameters, so LSystem parameters. So by default, they will be an attempt to load them from a file, but if the file does not exist, a curve and a scalar object will be created. So for the scalar object, we have some minimal and maximal value. Okay. Some color maps is defined, and then the rules. And the new thing is that we said that we want to use the parameters defined into the params object. to control the models. And so indeed, in addition to the 3D visualizations, you have the two parameters that are defined here. So you have first the scalar object, which was if I remind NB folial, and axis, the curve, which are defined here. And we can interactively modify them, and the 3D model is recomputed automatically. Okay. We can change the scalar value that will create more and more folial on the model. Okay. And so this is because it's a simple models, the visualization is quite interactive of the change of the parameters. At the end, if we want, we can directly save them into a files to reload their actual value for the next time the model is played. Okay. So this was for the graphical parameters. Oops. Now I wanted to show you another example, which is the creations of workflow for plant models. So in this case, the idea is to decompose the model into submodules and to play the different submodules and pass one value to the next one every time it's needed. So there is a long traditions of workflow in the FSPM community, in particular with the definition of OpenLAR. It allows to create modular, reusable components for plant simulations and to organize the different aspects of the simulations. The problem is that it has been defined in OpenLAR with specific software that can be played only inside onto a personal computer and not easy to play online. So to integrate it into notebooks, we started with we try to re-implement this and integrate this into Jupyter. So for this, we use an existing framework, which is Xores SimLabs, which allow to define components with input and outputs and function to process them. By default, the input and outputs are NumPy arrays. And so this means that you can process those values more efficiently. And so we needed to create some link between NumPy arrays and L-system structures. By default, the Xores SimLabs allow automatic computations of the dependencies between processes. So if one input of the one process has the same name as one output of another processes, then automatically they will be linked and so on. And at the end of the simulation, you have a large data set that allow to retrieve all the steps of the simulations. And so with some classical visualizations tools, you can easily explore and display the result of the simulations. So to define a process, this is quite easy. You will create a class and you will give him a decorator, XS process, that will make it possible to declare a number of aspects of the process within the Xores SimLab database. Input and output are declared with some names that allow to retrieve them later in the simulations. And basically, a process consists of a run step function and possibly an init function that will be run at each time step. A model of Xores is simply a set of processes. The workflow can be visualized and run, and you can have some functions to create visualization during the simulation. Okay. So what we did to integrate L-system within this framework is to start from simple L-system models and pass this file into a specific command, so XS _LPy process that will parse actually the model and deduce all the input and output. So the external commands that define somehow what are the possible external parameters of the model will be so parsed, and this will become input of the model. The output variable will be all the modules and their different parameters. So every parameters of modules will be exported as specific arrays. So for instance, you will have a metamer underscore t modules array that will contain all the t value of all the metamer of the simulations. By default, you will have also an export of the geometric representation, so the L scene, and the topological representation, so the L string of the simulation at each time step. So I will try to make a demo of that. Okay. So here is classical imports. And then I will create my model. So in this case, we create a number of graphical parameters, the actual models. So again, it's the growth of a growth unit. The main difference is that the number of function will depend on the lighting and the carbon allocation that will be made for each leaf. Okay. The L system based process is created here. Then a light process is created that will compute onto the geometrical representation of the structure light intersections, and a carbon allocation will take this as input to compute how much carbon is allocated to each organs. So the model is created from these three processes. Some output functions are defined at the end of the simulations. So we want to know what will be, for instance, every metamer size at the end, at every time step. So this is when we said this is a time stamp, and so on and so forth. We can run the simulations. The color of the leaf corresponds to how much light they are intercepting. At the end, you retrieve the data set, so DS out, and can ask, for instance, how much light was intercepted by each metamer at through times, how much carbons reserves was used, and so on and so forth. So very simple command lines that allow to plot several aspects of the model, which are stored into this data set of value. Okay. Just to mention that a very complex model can be created. So for instance, we build FSBM model of mango tree developments. So for this, a large number of parameters were defined, complex cell system rules also. And at the end, we have also a complex 3D representation, but the systems allow to generate and visualize this without problems. Against different aspects of the model can be visualized easily. Thanks to the X-ray SimLab structure, we can plot what is the general workflow. We can define and plot what is the general workflow of the models. So different aspects of the model are differentiated and potentially can be reused for other models. In this case, we reuse only the parts that simulate the growth of fruits and simulate it onto a static structure that was measured. Okay, and so this makes it possible to test several hypotheses on the autonomy of a branch of fruiting branch structures. And so this is made possible just by reusing only one part of the model and without changing too much things in the model. As the last illustrations, we plotted different stage of development of the tree, and this makes it possible to create some scene which look like an orchard. And as you can see, so this is a recording of the visualization, and as you can see, this is quite interactive, even if the number of details of the simulation is quite high. And so if you have a computer that allow rapid rendering, then you don't suffer from the fact that this is distributed visualizations. Okay, sorry. Okay, so now talking about reproducibility of all of that. So once you have created models, you want maybe to distribute it or to make some demo to others. So for this, we use the Conda software management system that allow to clearly define a number of software modules and the dependency of a model to those software modules. So for this, only with an environment files, you can define the dependency. And for our own packages, we use a continuous delivery systems where all the source code is managed on GitHub. Every time a new change in the code is made, the code is recompiled onto servers, and if needed, a package is created and can be deployed onto directly the Conda package management. This is very nice because this gives some visibility to the user of what is the status of development of these different software modules. Okay, and so as I said already, for a given model, you just need to create an environment.yaml files where you will specify what are the dependencies, the software dependencies that you use for these models. And just thanks to these files, the model can be run, for instance, online with a binder, for instance, or others. So as a conclusions, I tried to show you that FSPM can be integrated within notebooks and allow some interactive distributed visualizations and modelings. Thanks to Jupyter, we can benefit from all the advanced modeling tools of this community because new software modules comes every day. It allows also to create a collection of models and tutorials and put it online and make it possible to play with them really easily. This is, of course, a step forward for reproducible research in FSPM, as you can now specify directly what are the software dependencies and potentially directly into the notebooks describe the hypothesis that you made onto your models and even save the intermediate result and the final result directly into the notebooks. So now into a models, you can store quite all information that are required. Some limitations still for notebooks. When you use them, actually there is a sequential order of cell, but it's not mandatory that every cell are play one after another. And sometimes you may want to replay one previous cell that will change somehow the status of the the variables of the simulation and so on and so forth. So this can break somehow the consistency of the simulations. So there is a number of rules that so even if you have generated a complex notebooks, it's not totally clear if the results that are displayed into the notebooks are the ones that you can obtain by running it cell after cell. So we need to have some sort of a test of the notebook afterwards. And also, even if we put as many information as we can into the project, you may rely on some external source of data. And so potentially some aspect of the model may be lost if the link to the external source is lost. And so for this, again, we need to put some sort of guarantee that the source can be refound. So for instance, using some fair approach, but this has to be implemented more strongly into our framework. Okay. I think I try to present you all of this. I thank you very much. And
thank you very much, Frédéric. Actually, this shows very clearly the huge potential of using L systems under these notebooks. I would have a couple of questions related to the use of the notebooks, because you have been working on this in the last couple of years, I think.
Yes.
So you have already some experience with this. And I was, the first question is it completely equivalent at the moment if I want to use maybe the more advanced features of LPy? Is it completely equivalent to use a notebook system, the one that is currently implemented, and the let's say the more standard IDE interface?
Yeah. So yeah, actually, so this is a work in progress, and no, it's not true that all the feature of LPy Studio has been integrated into notebooks. So as you saw, you have some graphical interaction possibly, but some of them are not possible. For instance, you cannot edit a patch directly into notebooks for now. We will do this in the future, but for now it's not made. I think to debug a model in LPy, you have a studio, you have a number of features such as line highlighting and so on. So this is not as advanced into notebooks. Yeah, so not everything is implemented. And I feel for now that the two systems are made for somehow complementary but distinct approach. If you want to make some tutorials on LPy, I think notebooks are much better than LPy Studio. If you want to integrate different simulation with different aspects, the approach with notebooks that we propose is better. But if you want to create a complex models of complex L system models, I think for now LPy Studio is still more dedicated and so more easy to use. But,
did you see already, because you were experiencing both ways,
yes.
Is it clear for you what sort of interaction you would like to have with an editor, let's say the usual editor, that is not possible with the Jupyter Notebook, for instance? Is it something that is clear, or whatever you want to do not in terms of high level functionality, but in terms of interaction with the system? Are there things that you can do in Jupyter that is not possible to do in the editor? And this, I think, it's more or less obvious. Like the narrative approach is possible in the notebook, whereas it is not possible in the editor. But how about the opposite? Are they for what type of interaction? For what type of interaction would you need, or the narrative approach is not well suited?
No, I think if the health system model is large, if in terms of number of line of codes, it's not as trivial to go through the web page and go up, and find where the error is. And in LPy, within LPy, is easier, I found. But yeah.
Okay, so it's I understand that if you have a complex system, you explore your complex system using the narrative approach by expanding the length of the text, let's say.
Yes.
And it becomes a bit difficult to handle all this when the length becomes quite huge. Whereas if you are interacting with your machine, like in the usual editor, you would find it more natural. Is that what you mean?
Yeah, I had this feeling. This is maybe this is also personal, but I found I had this feeling, and I also had this feeling with the students. Yeah. As soon as the model is short, they are very confident with the notebooks, and they can go from if on the same web page you have several models, they can go from one to another and so on, and it's very easy for them. If you have in one page a very large models with different aspects and so on, somehow they can be lost a bit.
Okay.
Yeah.
I had a question also with the complexity of the data that is transferred, that is streamed online.
Yes.
If the model gets really big, really huge, like a tree can grow very fast, is it still convenient to you? I mean, is there any bottleneck with the streaming of the data between the client and the server?
Of course, if the simulation if the tree is huge, for instance, the plant is huge in terms of detail, there is always a bottleneck, I would say, in terms of memory.
But the limit is a bit so far that you don't even consider it, or it happens quite rapidly, actually.
No, I would say it is not. From what I see, it is not a huge problem. Like you even with the standard computer, you have a limit because graphical cards cannot support trillions of triangles. And so maybe it's not trillions with this approach. It's only, I don't know, millions. I don't know. Because when you discretize some of the representation at the end that we have, sometimes you have really a huge number of triangles. But the fact is that it is streamed into a really compact representation. So yeah. Of course, you have a problem, but this doesn't look like really a bottleneck of systems. In general, we feel confident enough.
Okay, and maybe a last question about the users, the current users of LPy, where they, when you presented this new way of programming plant development to different communities, were they using it? How are they welcoming this type of new way of programming? Do you know if some people, they really change their habits and they move to this new way of programming? What is the current trend about this? Do you have any feeling about this?
This is a very good question. I would say that, so I tested more onto students. So on the class I give to the university and so on. And in general, they are quite welcoming this this new approach. When I presented it to other researchers, in general, they are very enthusiastic. But I don't know if they are using it. But I don't know either if they are using LPy also. Like.
Yeah, but I was thinking about different groups that you know are
using. Yeah, are using. But I think people that are using, they are using. For some project, like if they have some project where they have to make a new model. Some of them will use that, and they have. But for people that have already their model set up with a previous approach, they didn't make the move to this new framework.
Okay.
But I feel this is mainly due because they don't have time or resources to make the change. But
Okay.
so I think, so basically what I want to say is that maybe this requires a bit of time to see the impact of this new approach. And because it is new, it has been presented in FSPM 1.5 years ago. And so for now, I didn't make some sort of poll to see if people has changed their habits or not.
Okay. Okay, so thank you once again, Frédéric, for spending the time with us. Hope this development that is super exciting on LPI and all the new technology that you are exploring for us will progress well, and you will have news for us in the
sure.
upcoming future. Thank you very much, Fred.
You're welcome.